So earlier we've used integrals to describe the area underneath a curve, specifically the area between a curve and the input axis, usually the x-axis. So we're going to extend that idea at the same time that we extend this idea of using an integral to sum up the areas of infinitely many rectangles, to find areas of figures that have more complex boundaries. So here you can imagine, so example one, we're going to find the area of this blue shaded region. The curve up top is y equals secant squared of x. The curve at the bottom is y equals sine of x. And I've shaded in the section of that graph that's in between x equals 0 and x equals pi over 4. So a couple ways to think about this. I might have asked you back in chapter 5 even to find this area. That's the area under the secant curve, under the secant squared curve between 0 and pi over 4. And you would have just written this integral from 0 to pi over 4 of secant squared of x. Well, now you can imagine that the shape that I want, the blue shaded, is really what I just had shaded in dark blue minus that area, which is the area under the sine curve between 0 and pi over 4. So this one way to think of this problem is, could you find the area between the x-axis and the upper curve and then subtract out sort of that blank space that I've colored in red? Or I want to think about this using rectangles too. Imagine I'm going to draw in infinitely many, infinitely thin rectangles. I'm going to use vertically oriented rectangles because that's all we've used so far. Imagine drawing in these rectangles. And those rectangles they have that length, that height that I'm drawing, and they have a width that's infinitely thin. If I tried to add up the areas of all those rectangles, watch what I would be doing. I'd be finding the integral from 0 to pi over 4. Every time I drew one of those red vertical line segments, the length of that is whatever the top y value is minus the bottom y value. So that point minus that point. When I subtract them, I'm going to end up subtracting the top curve minus the bottom curve. And that's going to be secant squared of x minus sine of x dx. So that's the integral I can write to find this blue shaded area. I'm going to switch boards and then show you how to integrate there. All right, so I'm integrating from 0 to pi over 4, secant squared x minus sine of x. Notice that I can choose to write that as one integral or two integrals. Either way, I'll get the same answer. My next step is to find an antiderivative. The antiderivative of secant squared is tangent. The antiderivative of negative sine is cosine. And I'm going to evaluate that antiderivative from 0 to pi over 4. So it's tangent of pi over 4 plus cosine of pi over 4 minus, and notice the brackets here, tangent of 0 plus cosine 0. So tangent of pi over 4 is 1 plus cosine of pi over 4, radical 2 over 2, minus tangent of 0 is 0, and cosine of 0 is 1. Feel free to leave your answer like this on the AP test, or we can simplify. That's 1 plus 2 square root of 2, plus square root of 2 over 2 minus 1, which gives a final answer of square root of 2 over 2. So this technique of finding areas in between curves, big idea for 7.2. You've probably seen in your free response notebook. There's a question on this topic every year. Here's the next problem. This one comes from your textbook. Here the difference is, I still have two graphs, and I'm trying to find sort of the area shaded in between the two of them. The difference here is it's a little less clear to me where the shading starts. I'm going to have to do the work to figure out the smallest x in the picture, the smallest x that got shaded, and the biggest x. In the first problem, they told me find the area between x equals 0 and x equals pi over 4. Here, I can tell that the two graphs meet, but I'm going to have to figure out where they are. So that's an algebra problem. So to find the intersection points of those two curves, I'm going to solve the equation that sets the two functions equal to each other. So here's my work. The two graphs are 2 minus x squared and y equals negative x. So I'm going to start with that equation, 2 minus x squared equals negative x. I notice that equation has degree 2. The biggest exponent is 2. And the way we solve degree 2 equations is to move everything to one side, so I have a 0, and I can use the zero product property. So I just moved everything to the right so that I would have a positive x squared term. I need two numbers that multiply together to make negative 2 and add up to negative 1. So I factored this as 0 equals x minus 2 times x plus 1. I'll just put this one more step in here in case we need a reminder. If two things multiply together to give a result of 0, then either the first thing was 0. So if x minus 2 is 0, that means x itself was 2. Or x plus 1 equals 0, which means x equals negative 1. So I get 2 x coordinates for 2 points of intersection. And that matches what I saw in the picture, right? There are 2 places where the two functions, the two curves intersect. So I know now that that x coordinate here is x equals negative 1, and this x coordinate there is x equals 2. Now I know my limits, and I'm going to be able to write my integral. So I'm going to integrate from negative 1 to 2. The top curve, which is the parabola one, right? So it's going to be 2 minus x squared minus the bottom curve, which in this case is negative x. That all needs a dx. I can simplify inside that integral as much as I want or as much as I don't want, but now I'm going to have to integrate. So I'm going to switch boards again to show you the integration process. There's my integral. The whole thing about chapter 7 is it's a chance to practice all those antiderivatives we found in chapter 6. So like I say, you don't have to rearrange this integral, but I did. I'm going to rewrite that as the integral of negative x squared plus x plus 2. I'm going to find an antiderivative using the reverse power rule, and I'm going to evaluate that integral. Notice I have stopped evaluating here, which you might choose to do, or you might choose to keep going. You really have no obligation to on the AP test. So I'm going to be a good example for you and leave this unsimplified.